All right, welcome everyone. Today we're going to keep talking about sequences, and we're going to start kind of where we left off last time. So we're going to come back to this idea of alternating sequences. So we looked at this last time where we have this gadget -1 raised to the power n. And there's normally other ways to do this, but usually this is the term that really gives us an alternating sequence. And what do we mean by alternating sequence? Well, it kind of bounces back and forth between negative and positive values. So this -1 raised to the power n, perfectly good sequence, but it just bounces back and forth between +1 value and -1 value. So it just alternates back and forth between those two values. And we know this sequence is divergent because it's just going back and forth between -1 and +1, and it never actually settles down. So if we were to kind of look out really far along the horizontal axis in our graph here, we'd see that the same kind of pattern. The values just bouncing back and forth, and they're not approaching any one specific number. Now, as we're going to see, this -1 to the power n, it sort of complicates our sequence. So when we're trying to figure out the limit, when we're trying to do other calculations, this alternating piece, this -1 to the power n, we're going to want some way to possibly get rid of it. And the way to do it is with this theorem. So let's kind of read through this theorem again. I know we did it last time, but let's read through it again. And let's keep in mind, we're working with two different sequences here. So we have our first sequence, which is just the original sequence. So we're given a sequence with maybe some positive and negative terms. So this is just our original sequence, A1, A2, A3, and so on. Just our original sequence. And what we're going to do is we're going to actually we're going to consider a second sequence. And this is where we essentially take the absolute value of each term. So we form this brand new sequence. So we start with our first sequence, our original sequence, where the terms are just A1, A2, A3, and so on. And we form a potentially brand new sequence where we take the absolute value of each of those. So the first term of this new sequence is absolute value A1. The second term is absolute value A2, and so on. And so what this theorem says is if the terms in the second sequence, if all these terms approach 0, so if the limit of that absolute value of an is equal to 0, well then the terms in our first sequence also must approach 0. So that's what this theorem says. It says if the limit of the absolute value of an as n goes to infinity is equal to 0, then the limit of an as n goes to infinity must also be 0. So really what it's saying in terms of these two sequences is if the terms in our second sequence, in our absolute value sequence here, if all of these go to 0, well then in our original sequence, these terms must also approach 0. And this is going to help us kind of get rid of this alternating piece, because when we do the absolute value of a negative, it gets rid of the negative. So the absolute value is going to help us cancel this out for other sequences. And that's what we're going to see in example 6. So in example 6, we're going to do the limit as n goes to infinity of the sequence -1 raised to the power n over n squared. And we're going to calculate this limit. And when we look at this thing, it might be helpful to kind of break this, kind of separate it out a little bit. So we're going to look at -1 raised to the power n times 1 over n squared. And let's just consider what each of these pieces is doing kind of separately. So we know the -1 to the power n. That gives us the alternating aspect of it. And if we look at the graph of our sequence here, that's what we see. So we do see kind of this alternating back and forth, negative, positive pattern. So that -1 to the n is giving us that alternating negative, positive pattern. But this 1 over n squared, that's going to be shrinking down to 0. So as n gets larger and larger, the 1 over n squared is one of our c over infinity forms, so that goes to 0. And that's what we're seeing here in this graph. So we're seeing two things. We're seeing the alternating pattern, but then we're also seeing these terms in our sequence approaching 0, approaching the horizontal axis there. And on its own, this -1 to the n power kind of complicates things. So instead of calculating this limit directly, what we're going to do is we're going to use that theorem where we apply the absolute value. So instead, let's consider the limit as n goes to infinity of the absolute value of -1 raised to the power n times 1 over n squared. Now when we have multiplication, we can split up the absolute value. So we can consider this. So when we have multiplication inside the absolute value, we can split up our absolute value over that multiplication. And now this absolute value of -1 to the power n, we know -1 to the power n bounces back and forth between +1 and -1, but when we do the absolute value of that, doesn't matter. We're always going to end up with +1. So essentially what happens here is this just cancels out to 1. So just always 1. And then 1 over n squared, that's always positive, so we can drop the absolute value sign there. So we end up with just 1 over n squared as n goes to infinity. And this is one of our c over infinity forms, so we know this goes to 0. And the justification for that last step is this is a c over infinity form. And what we've just shown is that the limit of the absolute value sequence, absolute value an, we've shown that this goes to 0. So we can conclude that our original sequence must also go to 0. By that previous theorem. So if we do the limit of the absolute value of our sequence, and we show that the limit of those absolute value terms goes to 0, well then that previous theorem says our original sequence with the negatives in there must also go to 0. And we can see that from this graph. So in the graph here, we've graphed the larger blue dots are the terms of our original sequence, and then you can see the terms of just the absolute value sequence on this curve that's decaying down to 0. So our 1 over n squared sequence, what we got when we applied the absolute value, is on this upper curve. And what that alternating piece did is it took some of them essentially and made them negative. But altogether, what we're seeing is that even though those alternating terms are bouncing back and forth, collectively they're all still approaching that common value of 0. So the 1 over n squared sequence, which is really the absolute value an sequence, is everything on this upper curve. And then our original sequence is the larger dots. So you can see, even though they're alternating back and forth, they're still approaching 0. So that's how we're going to use that theorem. There's other applications as well, but that's one of our main applications here, is to help us kind of deal with those negative 1 to the power n terms. All right, so we're going to use this now to talk about geometric sequences. So this is an important type of sequence, and these are where we have a sequence of the form r raised to the power n, or more generally, some number a times r raised to the power n, where a and r are real numbers. They're constants. And really what's changing here is the exponent. So just a few examples. These are things we've seen before, but let's just write out a few examples. We'll write out the first few terms. So something like 1, 3, 3 squared, 3 cubed, 3 to the 4th. That's a geometric sequence. Maybe we start somewhere slightly different. Maybe we start at 3 and do 3 squared, 3 cubed, so on. That's a geometric sequence. Or maybe we have something like 5 times 3, 5 times 3 squared, 5 times 3 cubed. That's also a geometric sequence. So what you can see here is basically each new term of our sequence is being multiplied by an additional r factor. Just going up the power of this common ratio here, in this case 3, each step we make, we're multiplying by an additional 3. We're multiplying by additional r. So that's what a geometric sequence is the exponents are increasing. And as we're going to see, a geometric sequence converges when either the absolute value of r is less than 1 or when r is equal to 1, and then it diverges for all other r values. The a value doesn't really do anything. So a could be anything, doesn't matter for our convergence here. Really the only thing that matters for a geometric series or a sequence is when r is the r value. So maybe another way to think of this absolute value r is less than 1, you could think of that as being, use a different color. So you could think of that as being r is between -1 and +1. Can't be -1, but it could be 1. So we could combine these to say that r could be anywhere such that it's greater than -1 but less than or equal to +1. So these are the r values where we'll get convergence. Let's see what's going on though. So let's start with positive r values that are greater than 0. And what we can see here, we've graphed a few different examples. And the first example here is when r is greater than 1. And what we see in this case is all of the terms of our sequence fall on this exponentially growing curve. And so what happens is, in this case, the limit of Rn as n goes to infinity is equal to infinity. It's on this exponentially growing curve, and what we see is that as n goes to infinity, all of the terms of our sequence kind of follow along the curve and they just get really big. They go to infinity. In the case right here, this is where r is equal to 1, and when r is equal to 1, we just get this constant sequence where all the values are just constantly 1. So here the limit actually does exist as n goes to infinity, and we just get 1. And then finally, we see this other case, and this is where r is between 0 and 1. What happens in that case? Well, all of the terms of our sequence fall on an exponentially decaying curve. So all of these points, they're falling on this exponential curve, and that curve is decaying down to 0. So the limit of Rn, in this case, is equal to 0 as n goes to infinity. So we have kind of 3 different possibilities here, and it really depends on what happens around when r is equal to 1. If r is greater than 1, well, then the terms of our geometric sequence will blow up. It'll get really big. If r is equal to 1, then it just stays constant. It stays constantly 1. So the limit of Rn is equal to 1. And if r is smaller than 1, well, then it's actually just going to decay down to 0. And there's a special case worth mentioning, that when r is equal to 0, well, then r raised to the power n, 0 raised to an exponent, is still 0. So this sequence is just the constant sequence 0. And so if we wanted to graph it, it would look something like won't graph at all. So just the constant sequence 0. So in that case, the limit of Rn would also be 0. So what we're seeing here is that when r is greater than 1, our sequence goes to infinity. When r is equal to 1, the limit is equal to 1. When r is really greater than or equal to 0, but less than 1, well, then the limit, in either of those cases, the limit is equal to 0. So it's either just identically 0 or it decays down to 0. All right, so what happens if r is negative? And we're going to see very similar kind of patterns here, but we're also going to, because we're having a negative raised to a power n, that's going to introduce the kind of an alternating look to it. And that's what we see. So let's take a minute and just kind of look at what's going on here. And let's think about there's going to be 3 different cases here. So kind of see these dots up here. These are graphing an example sequence where r is greater or is less than -1. So the r value has is less than -1. Then we have when r is exactly equal to -1, and then we have the case where r is between -1 and 0. And let's look at what happens to each of these 3 different cases. So, but notice, in all of these cases, r is a negative value. And so the first thing we notice is we get that alternating look. So the first terms start off negative, then they go positive, then they go negative, back to positive, then negative. So we get that alternating look. We're bouncing back and forth between positive and negative values. So first, when r is less than -1, the positive values all fall on that exponential growing curve that we saw back here. So some of the terms are going to fall on that same exponentially growing curve that's growing positive. But when we introduce the kind of the alternating part, we're going to get these terms that also they're exponentially growing, but they're growing negative. So they're getting larger and larger negative. So some of the terms of our sequence are exponentially growing positive. The other terms of our sequence are exponentially growing negative. And so in this case, the limit of Rn as n goes to infinity does not exist. Because we have some of these terms that are getting really big positive, we have another portion of our terms that are getting really big negative. And it keeps bouncing back and forth like that between really large positive numbers and really large negative numbers. We've looked at this case when r is equal to -1. Where did we do that? Right here. So this is a geometric sequence. And we saw that it bounces back and forth between +1 and -1. And it never settles down, so it doesn't approach one specific number. It's just always back and forth between +1, -1. So that sequence diverges as well. And so in the case when r is equal to -1, the limit of our sequence does not exist. It's divergent. Our sequence diverges because, again, it's just bouncing back and forth between these positive and negative values, and they're not shrinking down to anything specific. But in the case where r is small, it's small negative. It's in between -1 and 0. Well, what happens is we do have that alternating behavior bouncing back and forth, but the terms overall are shrinking down to 0. So in this case, when r is between -1 and 0, the limit is equal to 0. So yeah, we still have that alternating where we're going back and forth between negative, positive, negative, positive, but overall these terms are shrinking down to 0. And that's it. And let's kind of summarize everything here. So we went through a lot. And it's worth taking some time talking about these geometric sequences because we're going to be talking about them quite a bit. It turns out these geometric sequences have a lot of applications that we're going to be looking at. So we really want to get the idea of what do these sequences look like, and what is the ultimate behavior of them when we talk about limits and convergence and divergence. So let's kind of break this down. And it might help to actually kind of draw a number line for the r values. And we saw that really things happen the behavior really changes around -1 and +1. So when r was, let's start with the positive values that we looked at. So when r was greater than 1, let's write out the intervals maybe. So what are our intervals here? Let me write that differently. All right, so we looked at values where r was greater than 1. We looked at r values that were between -1 and +1. And then we looked at r values that were less than -1. And then also what actually happened directly at -1 and +1. All right, so let's start with the r value when r is greater than 1. What happened there? And actually, we'll write this out as a case. Let's write this as cases. So let's do the limit as n goes to infinity of r to the n. And we're going to write this as just some different cases. So we saw that this limit did not exist. We saw that the limit of Rn could be 0. We saw that it could be 1, or we saw that it could also be infinity. So what were the cases where these different options occurred? So what we saw is it didn't exist if the R value was less than or equal to -1. So the R values when it was less than -1 and then also directly at -1. That's where we saw the limit of this sequence did not exist. It was equal to 0 if our R values were between -1 and +1. So the limit became 0 when we were in here, in this inequality in this interval for R values. The one lone case where the limit was equal to 1 happened when R was equal to 1. And then it was infinity when the R value was greater than 1. And so really what we're seeing here is this sequence only converges, it only converges to a number when we have these two possibilities. So r had to be greater than -1, but less than or equal to +1. The behavior changed slightly at r equals 1, but we still got something convergent. So the limit of this sequence only converges when our r values are between -1 and less than or equal to +1. But -1 gave us a divergent sequence. All right, so these were the kind of the different possibilities. So we want to keep these in mind. And let's look at an example. Let's look at an example, example 7. The last one we're going to do. Limit of the sequence -3 raised to the power n divided by 5 raised to the power n plus 1. And we're doing the limit as n goes to infinity. And what we see here is we see a number raised to a power n. So what we want to do, and we see that also in the denominator. So the first thing, what we're kind of thinking when we look at this, is all of the pieces that we have here are in the form some number raised to the power n. So our strategy is to try and rewrite this as one single number raised to the power n. So right now we have these kind of two different values being raised to the power n. We want to in some way combine them and try to rewrite this as one single number raised to the power n. All right, so how are we going to do this? Well, right now this 5 to the n plus 1 is giving us some trouble because that plus 1. So we really want everything in the form raised to the power n. So what we're going to do is this plus 1 says we have an additional 5 factor here. So let's just separate that off. So we're going to write our sequence. We're going to rewrite it. We're just going to break this up. So it's going to be 5 times 5 to the power n. That's just an exponent law. So when we have addition in the exponent, that just becomes multiplication in the base terms there. So we've essentially took that extra plus 1 in our exponent and we've broken it off, and it becomes this 5 raised to the power 1 times 5 to the power n. All right, so once we do that, let's really separate this thing now. So let's really write this. Let's get that 5 out of there. So that 5 doesn't have a raised to the power n on it. So let's kind of separate that off. So we're going to have make it its own fraction. So we're going to have 1 over 5. And then let's get everything else that does have a raised to the power n. We'll get that in their own fraction. So we have this 1 over 5, and then we have this -3 to the n over 5 to the n. And we're doing the limit as n goes to infinity. Well, now in this fraction here, all of these things have the same exponent. So we can use one of our exponent rules that allows us to essentially factor off that common exponent. So there's an exponent rule. When we have a raised to the r divided by b raised to the r, we can essentially factor off that common exponent. So we get a over b all raised to the power r. And I guess good thing, let's go through. It's helpful to remember these exponent rules. So when we have, some number a raised to the r plus s, and the justification is actually not there, back here, that's equal to a to the r times a to the s. So when we have addition in the exponent, it becomes multiplication. All right, so that was our justification going from 5 to the n plus 1 to this 5 times 5 to the n. And now we've kind of we've gotten it into the correct form. So we wanted to rewrite this as r to the n, and that's exactly what we have here. And maybe one slight modification to that is maybe a times r to the n. So when we look at this, the a value is just some constant that's in front. And that's what we have here with this 1 over 5, is just the a value. And what did I do there? There we go. And then the term inside this power n, this is our r value. So we've rewritten it as kind of our general geometric sequence format here, a times r to the power n. And really, the limit of a geometric sequence, the limit doesn't depend on what a is, that constant multiple. We know we can get constant multiples out of there, out of the way. Really, all of the action is happening with this r to the n. So what do we see? So we see that r is equal to negative 3 over 5. It's the number inside this raised to the power n. So it's just the negative 3 over 5. And negative 3 over 5, if we go back to our previous result, negative 3 over 5 is in between negative 1 and positive 1, so the limit is going to be 0. So this value for r satisfies that inequality, where r is between negative 1 and positive 1. And so what we can say then is that the limit of this geometric sequence goes to 0. So we started off with this sequence, which wasn't quite written in the standard geometric sequence format. So that's what most of our work was just kind of getting it into this format where we have a constant times r to the n. And that's what we got. We got it as 1 over 5, the a value, times negative 3 over 5, all raised to the power n. And it was really that negative 3 over 5 raised to the n, that's really what determines what happens to our sequence. And so the r value there was negative 3 over 5. It falls in our inequality here where we needed our r values to be between negative 1 and positive 1. And so we know what happens to our sequence. It's equal to 0. All right. So that's going to do it for sequences right now. We're going to still be talking about these for quite a while. But in our next topic, series, we're going to see what happens when we try to take a sequence and add up all the terms. And really, this is where we're going for the next bunch of lessons, is we're going to be starting with the sequence, and we're going to try to add up all the terms and see if we can do it. And well, sometimes we can, sometimes we can't. And that's what we're going to be seeing. So, brace yourself. It's going to get exciting. So that's when we talk about series, which we'll start tomorrow. So have a good rest of your day, and we'll see you then. Bye-bye.